The multiverse is fun to speculate about, but hard to do proper science on. Today we have Daniele Sorini from Durham University doing proper science, examining essentially how many stars could form with different amplitudes of dark energy. This is relevant to a multiverse because of an old argument, essentially that most of the multiverse should have very large values of dark energy, but no life can form there. So we find ourselves in a universe with a small but non-zero value of dark energy. Small, but the largest value where life can form. Of course, this argument only works if life really can't form in universes with much greater dark energy than what we observe. Hence the need for hands-on research like this, asking how many stars can form when dark energy is different. However, beyond that motivation, Daniele's paper says something new about the anthropic principle and the value of dark energy that I've never seen before. Believe it or not, there is a lower limit on dark energy, below which life becomes less likely. Not impossible, but less likely. Yeah, a lower limit. And Daniela understands why. Hello, wonderful people, and welcome, Daniela. Do you want to start by telling us briefly about your paper?
Thank you, Sean, very much for having me. And sure, in my paper, together with John Peacock from the University of Edinburgh and Lucas Lombrizer from the University of Geneva, I've investigated the impact of the cosmological constant on past and future star formation. And in particular, I used my analytical model of cosmic star formation from 2021 to calculate the cosmic star formation history in flat lambda CDM models with very different values of the cosmological constant ranging from 0 to 100,000 times the observed value. And then I used the results to test anthropic arguments by looking into what values of the cosmological constant make the universe most efficient at producing stars, which are, of course, a precondition for the generation of intelligent observers like us.
We're going to try something a little different in this recording and probably from now onwards. Rather than making you wait to see the results, we're going to have a sneak preview of the results now. So what were the new insights you obtained and why are they important?
So the first key result is this. Here we're looking at the fraction of baryonic mass in a unit comoving volume that is converted into stars over the entire history of the universe on the y-axis as a function of the cosmological constant on the x-axis. So in other words, this plot tells us how efficient a universe with a given cosmological constant is at producing stars. Now, at higher values of lambda, there is a decrease in the cosmic stellar efficiency, and that is a consequence of the very fast acceleration in the expansion of the universe that kicks in so early that it makes it increasingly difficult for large-scale structures to form. So we will have fewer galaxies and stars. And we notice that there is also a peak in this cosmic stellar efficiency around 1/10 of the observed value of the cosmological constant, meaning that we are actually very close to the cosmological sweet spot, in a sense, for star formation in the universe. However, that does not mean that our universe is also the most likely to host intelligent observers like humans over its entire history, and I believe that this is the second most interesting insight from the work. So, if we assume that the likelihood for generating observers for a given value of lambda is proportional to the cosmic stellar efficiency that I showed in the previous slide, and if we follow Weinberg's argument calling for a flat prior for the cosmological constant, then we obtain a posterior for lambda given by this plot here. And as you can see, the peak of the posterior is at a value of lambda that is much larger than the one that we do measure. And so if you ask yourself, what is the probability of observing a value of lambda equal to or less than our observed value, then the probability that you obtain with my model is only 0.5%. So this would suggest that if one buys into the multiverse scenario, we would live in quite an unusual universe, and this potentially represents a challenge for anthropic arguments. But I need to stress right away that the results in this plot are heavily dependent on the assumed prior on lambda, and perhaps we can delve into that later in the discussion.
What was surprising to you about these results?
Well, I would say I was initially surprised by the fact that there was a peak at all in this plot showing the cosmic stellar efficiency of a universe as a function of lambda. I mean, as I explained earlier, I think it's pretty easy intuitively to see why for large values of lambda you would have a suppression in the cosmic stellar efficiency, but that's not as intuitive, at least for lower values of lambda. We can see in this plot that in an Einstein-de Sitter universe, the cosmic stellar efficiency is roughly a factor of 3 smaller than the one at the maximum in this plot, according to my model, of course. And actually, as we will see later in more detail, the point is that at lower values of lambda, what decreases the cosmic stellar efficiency is not really a suppression in structure formation, but it has to do with astrophysics. So the halos themselves become less efficient at forming stars. So at low lambda, the suppression is driven by astrophysics, at high lambda by cosmology. And so these two factors balance out at around, it seems, 1/10 of the observed value of the cosmological constant, which is thus, as I said earlier, the sweet spot that maximizes star formation in the universe.
Yeah, that's really interesting. So I'm really looking forward to discussing this a bit more, because it seems incredibly surprising to me that at 10 to the minus 4 of our measured value, which is a tiny fraction of our measured value, you're getting a fraction of 0.2, and then at 10 to the minus, say, 7, you're getting a fraction of 0.1. So that's a change in a factor of 2. Like, I'd have thought that 10 to the minus 4 would have already been essentially 0. And so the fact that there's a factor of 2 difference in a kind of observable quantity, the fraction of baryonic mass converted into stars, that feels like we should be able to kind of measure lambda by that observable in some sort of way. So that'll be an interesting thing to discuss later on as well. Yeah, let's go deeper into the background now. Why did you do this in a bit more detail, and what questions were unanswered that you wanted to solve, and why is this important and relevant in 2024?
Sure. Well, why I did that is because when I moved to Edinburgh for my first postdoc, John Peacock talked to me about how cool it would be to rigorously study the impact of cosmology, and in particular lambda, on the long-term star formation history in the universe, both past and future, and the implications for anthropic arguments. And I was very fascinated by the discussion as a cosmologist and also a researcher in galaxy formation as myself, because it really involves fundamental questions which have always captivated me. Why are we here? What is the origin and the long-term future of the universe? How would the universe be if it were different from some key aspect? So there's also a lot of implications for philosophy in this, and that's something that I really like. But after I read the literature on the anthropic argument, I realized how subtle the topic is and how little I knew, as it always happened. And so that made me more and more interested in it. And I importantly realized that you do not really have to adopt an a priori philosophical stance in favor or against anthropic reasoning. In fact, what I wanted to do in my work was to test it scientifically with the knowledge of cosmology and galaxy formation that we've developed so far. I have to say also that even if you do not really find all these philosophical questions fascinating, there are still scientifically good reasons as to why you should care about these sort of studies, both for galaxy formation and cosmology, as I'll explain now. So I start with galaxy formation first. So the ambition of a theory of galaxy formation in a cosmological context is to explain how an initially homogeneous, quasi-homogeneous density field evolved into the highly inhomogeneous visible universe that we observe today, where we've got matter concentrated in galaxies and separated by almost empty space. So while we do have now a pretty good understanding of how dark matter halos grow in a given cosmology, the challenge is still more the astrophysical one of comprehending exactly how diffuse gas is converted into stars within halos, and in particular, what is the role of stellar and AGN feedback in the process. However, this is quite challenging due to the expansive range of scales that are involved. In this slide, we're seeing an example of stellar feedback from supernova remnant in the upper part of the figure, and an example of AGN feedback in the lower part. So in the case of the supernova, we've got, features that are of the order of a few parsecs, but when we look at this image, which is an overlay from the Hubble Space Telescope plus the Chandra X-ray Observatory, observing a 10 to the 10 solar masses supermassive black hole at the center of a galaxy cluster, we can really see these lobes that are cutting through the intracluster medium due to the AGN-driven jet.
You've got it on the figure, but you didn't explicitly say it. It's 200,000 times bigger in scale.
Oh, yeah, sure. Yeah, actually, that was an important point. So, and the scale here is way larger than the one that you've got for the supernova feedback. We have 200 kiloparsec here. And now here is what feedback looks like in simulations. So the typical size of a full box hydrodynamic cosmological simulation is of at least 50 megaparsec. And here we've got an example from the SIMBA simulation. And in this inset, you can see a zoom on one of those features, which is representing an AGN-driven jet. And you can clearly see how pixelated this image looks on a scale of 1 megaparsec, and it looks much less resolved compared to the beautiful observational picture that I showed earlier. So the reality is that feedback affects scales that are orders of magnitude smaller than what cosmological simulations can typically resolve. So due to numerical constraints, it is just not feasible to represent these processes in a simulation from first principles. So you need to resort to some subgrid modeling that is based on numerical prescriptions that sort of describe the average effect of stellar and AGN feedback on the surrounding gas, etc. And this is based on numerical models, the parameters of which need to be tuned at some level to observations, and they can vary from code to code. So one needs to compare the predictions of the simulation with as many observables as possible to discriminate amongst the different models. So here is an example of what I've just said from a recent work by Lucy Share, who was a former master student of mine, and she considered a suite of simulations from SIMBA, each with different feedback prescriptions, and compare them with data of the star formation rate density as a function of cosmic time. And we can see that the different runs exhibit different levels of agreement with the data. But the point is that even for the runs that have the best agreement with the data, the parameters underlying the corresponding stellar and AGN feedback prescriptions are themselves tuned to reproduce some other independent observations from the one that I showed here. So the issue here is that we can have the legitimate concern that feedback parameters may be overly fine-tuned to our own universe, hence implicitly assuming our own cosmological model. So you could ask what happens if we change the cosmological parameters by a lot, even to values that are not corroborated by observations, and in a way use these numerical thought experiment as a stress test of our galaxy formation models, and see if that can reveal any significant degeneracy between cosmological parameters and astrophysical processes in determining the feedback subgrid models.
You haven't kind of defined the y-axis here, but I guess it should be relatively self-explanatory. I guess it's amount of stellar mass per year per volume of megaparsec that is kind of being produced.
Yeah, exactly. It's exactly that. So yeah, I think the point here is that even if one forgets anthropic arguments, it is still super interesting to study star formation in counterfactual cosmologies for the sake of galaxy formation itself.
To maybe rephrase that in different wording, what you're saying we should be worried about is, like, let's say we double lambda. If we then find that we can still kind of fit these data points by changing the feedback and the AGN and the jet parameters, then we should be worried about this overfitting, that we're not necessarily getting the correct subgrid prescriptions by fitting to these data points, because it could be that there are degeneracies with other cosmological parameters.
I think so, yeah. In principle, there is that concern. I have to say that also of other works that I know of, when they considered a suite of simulations also with different feedback prescriptions and different cosmologies, if you change the value of the cosmological parameters within something reasonable based on our observations, things seem to be pretty robust. But this is more a conceptual exercise of understanding how special the parameters are for our own universe in a way. But then, of course, there is also the second motivation, which is more cosmological. So we know that the Lambda CDM model, despite recent tensions, H0, S8, and recent SE measurements on the equation of stellar energy, it still represents the standard cosmological paradigm. However, the Lambda CDM paradigm itself cannot tell you what lambda exactly is. We know that it's a constant that we can include in the Einstein's equations, and depending on the side of the equation where we include it, we can give different physical meaning to it. If we think of it as a form of dark energy, for example, there are also many different models that try to make sense of that, and I don't have time to go through all of them, of course. But we also know that our current understanding of fundamental physics does not really allow us to predict a value of the cosmological constant that is close to the one that we observe. There is a 120 orders of magnitude discrepancy. That's the number that is usually quoted between the predicted and observed values. Now, there are other works that argue that depending on how exactly you make this calculation, maybe you can get it to something as small as only 10 to the 15 difference, but I mean, it is still a lot, right? We clearly have a huge discrepancy. So the main point is, no matter how you look at lambda, it is puzzling that the observed value of lambda, whatever it represents, is so low compared to our theoretical expectations. Even more so if you consider that the small but positive value of lambda gives rise to coincidences that cry out for an explanation, and the most famous of which is the fact that at present time the lambda energy density and the matter energy density are of the same order, whereas in the past and the future of the universe one of the two dominates over the other. So given the current difficulty in trying to explain lambda from first principles, of course, we should do much more research in that direction as well, but one could also take a different approach and try to rescope the question, and instead of asking what is really lambda, you can ask, why does lambda have the value that it does? Can we explain somehow the observed value? And if we don't want to do it from first principles, another approach is the anthropic approach that seeks to address this reduced but still fundamental question on the value of lambda by exploiting our own existence as a data point. We know we exist, so our cosmological parameters, including lambda, must allow for the formation of large-scale structure, galaxies, stars, habitable planets, and ultimately the emergence of intelligent observers such as ourselves. So this, in a nutshell, is the idea that was first introduced by Carter in 1974 and is known as anthropic principle, with certain subtle variations that we can gloss over now. More radically, perhaps, one may also consider a multiverse ensemble of universes with different physical parameters. Now, an ensemble of causally separated bubble universes is an inevitable prediction of models of stochastic inflation, where inflation is eternal, and field fluctuations across the different bubble universes can readily generate different values for the fundamental constants within them. So in this case, one needs to estimate how these bubble universes are populated with observers for different values of lambda. And this is basically what Weinberg did in 1989, and his argument was, among all possible values of lambda in these ensemble of universes in the multiverse, only a tiny fraction of them will be able to promote the emergence of life. And the reason is that if you've got a value of lambda that is too high, then, as we were saying at the beginning of our chat, the acceleration of the universe would kick in so early that it would make it at some point impossible for matter to coalesce and form halos, galaxies, stars, planets, and so on and so forth. Now, one might think that this argument applies only if you accept the existence of the multiverse. But actually, even if we do not think about a real physical multiverse, we can still make this argument by considering hypothetical different universes and hypothetical different lambdas. So making some sort of a thought experiment on how the universe would be if lambda were different. So we could still assign a probability to the generation of observers with many caveats in a Bayesian sense.
When you say in a Bayesian sense, one still needs that prior distribution. I mean, one can calculate exactly what you have calculated in your paper, the star formation rate as a function of lambda. But I guess you then need to say, what is the prior distribution on lambda? And it kind of feels difficult to me to do that without a multiverse. Whereas if there is a multiverse, I can imagine there existing a prior probability distribution. But I guess this is getting into the weeds of philosophical interpretations of probability, perhaps.
I think that even if you don't ask yourself whether these universes exist or not, the meaning of prior, the way I understand it, is what is your prior knowledge of that parameter. So if you do not know what lambda is, you would just go for a flat prior. And more precisely, if we consider again Weinberg's argument, from a physical standpoint, there is no compelling reason for preferring a small but positive value of lambda to lambda equals 0, so you would expect to have something looking like a flat prior, at least close to lambda equals 0.
Yeah, normally people talk about this flat prior all the way up to 10 to the power of 120, which just corresponds to the Planck scale, and the argument there is that there would be potentially quantum gravity scale fluctuations in the vacuum energy that might be kicking in at that level. That often comes across as kind of pie in the sky. Okay, well, you're just making this number up. We don't know anything about quantum gravity. But even the standard model Lagrangian has a bunch of terms in it. Those terms have to very, very delicately cancel to get the vacuum energy to be less than the electroweak phase transition energy scale, less than the QCD energy scale, which is already many, 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 many orders of magnitude larger than the observed value. So even if we ignore this 10 to the 120 value, and maybe this is exactly what on your previous slide the 10 to the power of 15 was, but those are the sort of unavoidable things. Either the standard model parameters are just happening to be so perfectly tuned that the vacuum energies all perfectly cancel to be nearly 0, or there is some other reason why the vacuum energy is not causing physical effects. But if it's not causing physical effects, why are we measuring it to have this particular value that is so small? If anyone's super uncomfortable with anthropic reasoning, I don't know, like from my perspective, I guess maybe it's quite similar to your own one. It's like if it happens to be that this is the correct reason why lambda is small, then I want science to be able to study it. But maybe a more, I don't know, mundane explanation might satisfy you, which is, why is the Earth the distance from the sun that it happens to be from the sun? So you could come up with all sorts of, and people were, before they discovered there is a galaxy and there is a universe, people were trying to come up with all sorts of symmetry arguments back in the 19th century and such about why the Earth has to be this distance from the sun, because, you know, if it goes further away, it'll get pulled back in. And it just turned out that it is an anthropic reason. There are many planets around many stars in many galaxies, and we're only going to live on the one that happens to be the right distance to have liquid water, blah, 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 blah. So there is already a anthropic explanation for that fact, the Earth's distance from the sun. And so maybe not, maybe yes, this is also the case for the value of lambda.
No, I agree. And actually, the distance of the Earth from the sun is one of the arguments that I often use as well. The point is that we already use anthropic reasoning also in other parts of science at some level. We were talking about priors, right? And so indeed, you need to assume a prior on lambda at some point, and there has been also already some work with cosmological simulations. For example, Barnes et al. In 2018, who used different variants of the Eagle simulation with lambda equals 0 to our own value and many larger multiples thereof. And they looked at the star formation rate per unit baryonic mass as a function of cosmic time. And as you can see, for larger values of lambda, this function seems to be suppressed. Note that they also ran the simulations into the future of the universe, because in principle you cannot exclude that star formation goes on also after our present time, and may contribute also significantly to the total star formation count of the universe. And they use these functions as a proxy for the likelihood, that is to say, the probability of generating observers given a certain value of lambda. So having that plus the prior on lambda, then you are able to define the posterior, as I already mentioned earlier.
When you say they use that figure, do you mean like the integral of that figure, the sum of that figure over all time? Or?
Yeah, okay, I did a bit of a simplification in that slide, but I think what they did was they had that probability as a function of lambda and t, and then they were integrating things later. So I don't remember exactly how they did the integral there now on top of my head, but yeah. So, and here's the posterior, and the blue line and the blue dots are the results from the Barnes et al. Work that I showed earlier. There is also another work with different simulations based on the ENSO code, which is this red line here by O et al. 2022. And here I'm also showing the results from an analytical model by John Peacock from 2007. And you can see that in all these three cases, the peak of the posterior actually happens to be at a value of lambda that is much larger than the value that we do observe. So that if you ask yourself what is the probability of observing lambda less than or equal to our measured value, then you've got something that actually fluctuates between 2% and roughly 13%, depending on the model that you consider. But in any case, we happen to be in the tails of the distribution. That's something that all these models seem to agree on. They do not agree on how much in the tail we are.
I presume these all use uniform priors from 0 in a linear scale up to 10 to the power of some large number.
Yes, exactly. And also this work inspired my paper a lot. And so, for example, what I wanted to do is that to overcome some limitations from the simulation works. Of course, simulations are great at giving us a very accurate picture of the astrophysics of star formation, but due to numerical constraints, even if you run them into the future, at some point you have to stop. I think the simulation that reached the latest time was around stopped at around 100 giga-years from now, but you don't know if there is, also further star formation going on even after that. Also, the volume of the simulation is limited, which means that you cannot probe very massive halos that could be rare but could also contribute to the stellar mass density of the universe. So I wanted to use an analytical model that can be used to make predictions at arbitrarily large times and doesn't have all these box size issues. Of course, I needed to inevitably simplify the physics, but in a manner that I believe is quite reasonable based on the agreement with observations for the past and present star formation rate density, as we will see later.
Okay, awesome. Yeah, let's get into the details about how you went beyond the simulations and what your model is built on, and then how we get to that star formation curve you showed us at the beginning.
First of all, I need to determine the cosmic star formation rate density as a function of cosmic time. That is to say, the amount of stellar mass produced per unit time per unit co-moving volume. And that is essentially a counting exercise. So we know what the matter density in the universe is, and then we need to ask ourselves what is the fraction of the matter in the universe that ends up in collapsed structures, that is to say, dark matter halos. And that is given simply by the halo multiplicity function. And of course, we can use some analytical model for that. For example, Press-Schechter, or as I did in my work, Schatten-Thoman. So that is actually the easy part of the business. But the difficult part comes next, when we want to know, out of the matter that has collapsed in halos, what is the fraction that forms stars. So we can represent this with a function of halo mass and redshift, and we call it the normalized star formation rate. So basically it's the star formation rate divided by the total halo mass in the halo. And when you multiply these three factors, by definition, that gives you the star formation rate density in a halo of total mass m at redshift z. So now, if you want to know what is the total cosmic star formation rate density, then you need to consider halos of all masses. So you just need to integrate this over the halo mass. And that's basically the core formula of my model. So we discussed already how we do the easy part for the halo multiplicity function. So let's have a look at the hard part, the star formation rate.
Can we maybe pause very briefly on the yellow, or the orangey part, the co-moving matter density? Have you just fixed that to the observed value as you change lambda, or?
Oh, that's a good point. No, actually, we designed the ensemble of universes such that at very early times, all universes will look the same. So what we do is we go very much in the past, where matter dominates, and we just rescale lambda by a factor at early times, and then we re-evolve that to present times and also beyond, as we will see.
That seems a well-motivated way to do it. Are there other well-motivated ways that might change the story?
Yeah, well, there could be also different ideas on how to model this multiverse ensemble, where you could have some more complex interplay between how you vary lambda and omega matter. You could also think of changing more parameters independently simultaneously, and that's something that we are leaving for future work. So basically to rescale with two independent factors at early times, matter and lambda, so that could change things potentially more significantly.
And then you'd have to worry about the prior probability distribution on the matter as well, I guess.
Yes, exactly. That's why we started with one parameter, which was already way more difficult than we thought. So yes. Here, I've developed an analytical model of star formation that generalizes the work by Hernquist and Springel from 2003. And the idea is that within each halo, the normalized star formation rate is limited by whichever timescale is the shortest. At high redshift, it is an internal gas consumption timescale, and at low redshift, that is the cooling timescale. Now, within Hernquist and Springel's model, at high redshift, the star formation rate is easy to calculate. It's given basically by the gas mass divided by the timescale that I mentioned, whereas at low redshift, the cooling time is a little bit more tricky to calculate. But the idea is to still have a toy model to determine the cooling rate, where we consider a spherically symmetric halo, with a power law gas density profile within. And then we've got a cooling front that expands from the center outwards. So all gas within the cooling radius of this front becomes cool and stays cool thereafter. And the cooling is determined by the cooling time, which in turn depends on the local gas density and the cooling function. So in the end, the gas cooling rate is a proxy for the star formation rate at low redshift. Now, so far, I followed exactly the original Henquist and Springel model, but they assumed a constant baryon mass fraction within halos, and the baryonic mass within halos is basically the fuel for the star formation, whereas I dropped this assumption, and I've introduced a simple constant wind model for supernovae-driven winds that pushes the gas outwards, and so there is basically a boundary where the outward pressure due to these winds balances the gravitational pull, and then I say whatever gas is within this critical radius stays in, and the other gas is unbound from the halo. And interestingly, if I do that, I obtain a first principles prediction for the baryonic Tully-Fisher relationship, essentially, which is the correlation between the baryonic mass of a halo and its total mass. And it turns out that you can match the observations quite well. The other thing I did was just dropping all assumptions in Henquist and Springel that were based on something special about a given epoch of the universe in the past or the present. Because my interest was to make this general and extrapolate it to the very far future. So after I've done my modifications, here you can see the different predictions for the star formation rate density in the original Henquist and Springel model, which is the dotted blue line, and my own model, which is the solid red line. And here I also compare these not only with observations, but also with predictions from the SIMBA cosmological simulation. And you can see that with these modifications, the model has a better agreement with the data within a factor of 2, which is actually of the same order of the agreement that even full cosmological simulations can provide with the data. But of course, my model, being analytical, is not as expensive to run.
I guess it does equally well until you get to maybe about 10 to the 9 gigayears. Then maybe it starts to overpredict. Is that a fair?
Yeah. I mean, the slope there is less steep. It is still reasonably within the error bars from the data, if you consider like 3 sigma.
But it still does much better than the original model, because the original model is also overpredicting there.
Yes, at late times the model overpredicts star formation rate density and is also less steep. However, the agreement is still within a factor of 2, which is not worrying compared to the conclusions of the work.
The reason it might have been worrying would be if most of the star formation was happening at that late time. But I guess given that the y-axis is logarithmic, most of the stuff is happening earlier on. That's where you want to be more accurate, and you clearly are more accurate there.
Yeah, in terms of magnitude, you've got more star formation earlier, but because you've got, an infinite time ahead of you, actually when you do the integral on the future star formation only, it turns out that can matter quite significantly for the overall star formation history of the universe. But even if we have, say, a difference of a factor of 2, airshift 0, and that stays the same for the future star formation history, then a factor of 2 for the total cosmic stellar efficiency of the universe does not matter much compared to the very sudden suppression introduced by large values of lambda, where you drop by several orders of magnitude in the stellar efficiency pretty quickly. And here is what I meant when I said that I extended the model in the future. So the y-axis is the same as before, now on a linear scale, and the x-axis is negative redshift, which actually is a trick to represent an infinite amount of time in a finite interval, because redshift -1 would mean time that goes to infinity. And you can see that, unlike the original Hemquist and Springal formalism, my model predicts a convergent star formation rate density as time goes to infinity, and even better, the integral over time turns out to be convergent, meaning that the total stellar mass density produced in the entire history of the universe is actually convergent. So that allows us to make anthropic arguments easily, because we can just recalculate the star formation rate density for different values of lambda. We keep integrating it until time that goes to infinity, and then we look at the stellar mass density that is produced and the entire history of the universe, and as a function of lambda.
It still would leave me a little concerned if this final value does kind of depend very much on the very, very tail of this distribution. There's an infinite amount of time there, but maybe it cuts off so rapidly down to zero that it doesn't affect the total number of stars, or does it? How much of your final total number of stars is happening after 15 billion years versus before?
The exact percentage varies according to the value of lambda that you consider. And it's actually, if I remember correctly, it's more important for higher values of lambda. Actually, this slide helps explaining visually what you were asking. Here we see the cumulative stellar mass per unit comoving volume produced up to a certain cosmic time, which is what we see in the lower x-axis. And the upper x-axis shows us the corresponding redshift in our own universe, because the tricky thing here is that the time redshift relationship is cosmology dependent. So the lower and upper axes are meaningfully related only for our own universe. Otherwise, you should just look at the lower axis that tells you the cosmic time in all the universes considered here. And clearly, every color refers to a different value of lambda. So we can see that all these curves for the stellar mass density actually plateau in the future. And here I put this break where you can see even, after several orders of magnitude in time, you don't have that much of a difference at that point. So that answers your questions. However, it's interesting to see that the plateau in my model occurs much later than the 100 giga-years, which was the latest time considered by O et al. 2022 ENSO simulations. So that's something to bear in mind.
Yeah, there's some weird, interesting things to unpack from this. So the black line being the largest value of lambda. I think naively, if you'd asked me to bet on whether larger or smaller lambda would plateau earlier or later, I'd have got it the wrong way round. I'd have thought that because the large value of dark energy is pushing the galaxies away, that it would mean that new stars, there aren't being new galaxy clusters forming from infalling galaxies colliding, so new stars would just stop forming earlier. What is your kind of intuitive explanation as to why, with a larger value of lambda, obviously the total value of star formation drops, but the increase carries on for longer? What is the physics behind that?
Yeah, so we'll see this also in more detail later, but the idea is that you've got overall fewer halos, but those halos that you've got are much denser, are much more concentrated. If you think of how galaxy formation would proceed there, you would have little halos would be like little island universes of their own, where you've got a lot of matter there and nothing outside them. And if you've got a very dense halo, then you've got a very high gas cooling rate that can keep producing stars until almost indefinitely.
It's also the fact that it's so low. It could actually be that, say, the green and yellow lines are also increasing by the order of magnitude of like 10 to the power of 5. It's just that at 10 to the power of 9, an increase in magnitude, so 10 to the 9 plus 10 to the 5 is negligible. You can't see any difference on the plot. But 10 to the 5 plus 10 to the 5 is large. You see a difference on the plot. Even if at a later time there are still of order 10 to the 5 solar masses per unit of volume being produced in a lambda equals 1 universe, you just wouldn't see any change in the green curve. But you do see a change in the black curve.
Oh, yes. Now I see what you mean. Yeah. That's also, that's a good point. Yes.
So the other thing that I thought was kind of very curious about this is the 10 to the minus 2 line, because it doesn't seem to be doing what, it doesn't seem to be halfway between what the yellow line and red line are doing, the 10 to the minus 1 and 10 to the minus 4. Why is that sort of orangey brown line have such a steep slope compared to the others?
So this has to do with the redshift evolution of the cooling radius that I talked about earlier. So the cooling radius tells you what is the mass of a gas that can cool and form stars, and basically there is a dependence of the cooling radius on cosmic time, that is approximately equal to the dynamical time at early cosmic times, but then it becomes comparable to the cosmic time at late cosmic times. So there is sort of a transition between these two regimes, which occurs at different cosmic times, and these departures from lambda equals 0, where there is no such transition at all, is observed exactly at the times where this transition happens. So that's why you see the 10 to the minus 4 departing here, and then you've got the 10 to the minus 2 departing earlier, and then when you go early enough, you cannot really appreciate this deviation anymore.
I've also noticed something that I think if you hadn't truncated the plot with this cut, I mean obviously you have to, because otherwise people's screens aren't infinitely wide, I would have seen that the red line actually does do this jump as well. It just does it later, because the red line on the right of the cut is up with everything else. So
exactly, because I need to,
I guess the other really cool thing that you can see from this plot is kind of exactly 10 to the minus 1, the yellow line gets to the top. But maybe curiously, it gets to the top late, right? Like at 10 to the power of 3, the green one is above the yellow one.
Yeah, it does indeed, yeah.
And I guess this is kind of your explanation of these jumps that the orange line and red line are doing and that the yellow line did earlier. It's kind of maybe getting into what you're perhaps about to get into, but how the astrophysics is also affecting, like the green one doesn't get as big of a bump as the other ones.
Yes, exactly. I think I'll provide a simpler explanation later, like more intuitive, but yeah. So at this point, we can just look at the values of these plateaus here and plot them as a function of lambda. So we take these asymptotic stellar mass densities and we can divide them by the Barion mass density of the universe, and that's the y-axis in this plot. So that's why this represents the fraction of baryonic mass converted into stars per unit moving volume over the entire history of the universe as a function of lambda, and that's the key plot that I showed in the beginning of this chat. As I said earlier, we see that there is this peak around 1/10 of the observed value of the cosmological constant, and now it's time to explain why these two suppressions occur.
And just a quick interruption, because I think I had a misconception when you showed this plot at the beginning that I think I don't have now, but maybe it's the other way around. The fraction of baryonic mass here, calling it a fraction is just a rescaling of the y-axis, right? It's not that at different values of lambda, the total amount of baryonic mass is different. It's actually the same for every single value of lambda. Because I got a little bit worried when you were showing this plot at the beginning that it, like, surely it's the total amount of baryonic mass converted that is actually relevant, not the fraction. And I was going to ask you a question about that. But given that the total amount of baryonic mass is the same for the whole x-axis, the fraction is then just a nice way of having sensible numbers on the y-axis instead of insane numbers like 10 to the power of 9.
Yeah, you're right, yeah. As we said already earlier, if we have very large values of lambda, then we will have fewer massive halos. And this is just a consequence of the freeze out of structure formation. Here we are looking at the halo mass function, essentially, more precisely the mass fraction in halos as a function of the halo mass, and different colors refer to different redshifts, different line styles to different values of lambda. And we can see that for larger values of lambda, we've got that the cutoff of the halo mass function occurs at smaller and smaller values. This means that you have fewer halos overall, and they will reach lower masses. But here we are looking at the asymptotic stellar mass fraction in halos as a function of their total mass. So with that I mean we integrate the star formation rate of halos of a fixed mass over the entire history of the universe, and we divide that by the halo mass. And every line here corresponds to a different value of lambda. And the interesting thing here is that when we go to large values of lambda, we've got that this plateau that originally appears only at intermediate, but also large values of lambda keeps becoming larger until at a certain point halos of almost all masses will have a very high star formation efficiency. So this could be a little bit counterintuitive at first, but now let's consider a halo with a fixed virial mass. Now if we calculate its virial radius, that will depend on cosmology, of course, and it turns out that it is actually larger in universes with smaller values of lambda. So this means that in a universe with lambda equals 0, you will have the maximum size for this halo, whereas for large values of lambda, this halo will become smaller and smaller. Put it in other terms, if the value of lambda is small, then the density of the halo is smaller, and so the gas density will also typically be smaller, so you will have a lower cooling rate. And similarly, for high values of lambda, you will have higher density, which makes it easier to form stars via cooling. And to have a more intuitive understanding of why that happens beyond this mathematical relationship between the halo mass, virial mass, and the virial radius, we can look at these beautiful images from the Eagle simulations from the Barnes et al. 2018 papers. And as you can see here, they considered one halo in the run with lambda equals 0, and at the bottom here you can see the cosmic time that they are considering. The color coding here shows you the gas density in the halo, where yellow is larger densities, and blue, purplish is intermediate, and this white thing here is very low density. So if we follow the evolution of this halo over time, we will see that it will form something that looks like a galaxy, is quite diffuse, and there's nothing strange with that. If we turn at our attention to a large value of lambda, for example 30 times the value that we observe, at early times it will look very much like the halo that we looked at lambda equals 0, because at early times we are in the matter-dominated era, so all universes should look the same, right? Now, if we continue over time, we can see that the assembly of gas in the halo is faster, and at a time that is comparable to present time, we find a very high density concentrated halo with almost nothing around it, and that's the island halo idea that I mentioned earlier. So here we've got very high gas densities that will give you also a higher star formation.
Can I try and just re understand the physics of that? It's because stuff that would have disrupted this and made it more diffuse got pulled away by the faster cosmological expansion.
Yes, exactly. Yes.
That like this seems like by far the most interesting result of your paper, I guess. This drop in.
Yeah, I found it very, very, very interesting. Yeah, I mean, yeah. Again, these images are from Bars et al. Paper, but yeah, they do not observe this drop, and we'll come back to that later. But yeah. So in conclusion, we can say that for high values of lambda, you will have very efficient halos at forming stars, but there will be really few of them, and that's what suppresses the cosmic stellar efficiency. Whereas for lower values of lambda, you will have more halos, but less efficient at forming stars. And there is a balance between these two effects that generates this peak at 1/10 of the observed value of the cosmological constant. So our own universe is within an order of magnitude of this peak, so to say. And in this sense, it is sort of special for forming stars. It's close to the maximum efficiency according to this model. Now, we want to convert this into a probability distribution for measuring a certain value of lambda given the existence of observers. So we assume that this is the likelihood for generating observers for a given value of lambda, and we also assume a flat prior on lambda, and if we do this, that's what we obtain for the posterior, which is also the other slide that I showed at the very beginning of this chat. We can see that the median of the posterior is around 500 times the value of lambda that we observe, and if you calculate the probability of observing a value of lambda equal to or less than the one that we do measure in our universe, that's around 0.5%. Now I understand that this can look a little bit puzzling, when switching from a graph where you've got the peak of the likelihood around our value of lambda, and here you find that the posterior has a peak that is much larger than our own observed value. But the tricky point here is that the prior on lambda does matter a lot. If you assume a flat prior on lambda, then mathematically you get an extra lambda term in the expression for the posterior that gives more weight to higher values of lambda. And this is not cheating, by the way. If we look at this plot here, because the x-axis is logarithmic, but we are assuming a flat prior on lambda, not log lambda, if you were to visualize this plot on a linear scale on the x-axis, you would have a very, 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 very long tail for high values of lambda. And so it does make sense that a lot of the posterior, that the peak of the posterior ends up being at high values of lambda.
The alternative would be if you plotted the prior on the log axis, it would be going up at high values of the x-axis. Yeah.
Yes, exactly. Yes. We've been talking a lot about the prior, so now it's time to open these kind of worms. The conclusions are actually very sensitive to the prior on lambda. So here, as an exercise, we just try to think of different priors. These are all power law priors that are designed to give more weight to larger values of lambda. And if you take, for example, a power law index of minus 0.9, then it turns out that our own value of lambda is roughly at the peak of the posterior. Now, I'm not saying that you should tune your prior in order to make the anthropic principle work. The prior should be given by your theory, in a way, by independent considerations. But this is just a caveat that the conclusions are very sensitive to the prior that we consider. I did not put a flat prior on log lambda because that doesn't make sense for lambda equals 0. So if you take a flat prior on log lambda, you are implicitly saying, no, there is a finite positive value of lambda below which we cannot go. So you need also to justify that.
You could do a 50-50, right? You could say there's a 0.5 probability of lambda being 0 and a 0.5 probability of it being a flat pariah.
Yes, you can also do that. If you did that, I suspect it would look like this cyan curve here or something similar to that.
But I do think if you're playing the interesting coincidences game, it is interesting that what you're calling the likelihood does have a peak, and that peak is close to our value. That didn't have to happen, right? Like you could have chugged through all the numbers and it came out that the peak was at 100 our value of lambda, or 10 to the minus 5 our value of lambda. It is very curious that it came out at 0.1 our value of lambda.
That I agree. So that even if you forget about the anthropic implication for a minute, just seeing that for the star formation itself, we are close to the cosmological sweet spot. That's really intriguing. Yeah, I agree.
I agree that you shouldn't try to save the anthropic principle by changing your prior, but on the other hand, if you're being a scientist and you're exploring all avenues, then the fact that a logarithmic prior with your likelihood, if we believe your likelihood, does have us at the peak, means that one could go looking now to see, okay, is there any well-motivated reason for a log prior? Like if you're picking scales out of a hat instead of picking the value of lambda out of a hat, you would probably want a log prior. So maybe the multiverse is populating these vacua where it's randomly picking scales, perhaps. I don't know. And then everything the whole puzzle resolves itself. But of course, yeah, maybe not, of course, as well. But that's very interesting.
So basically the point here, what we tested is that if we assume a flat prior on lambda with lambda varying between 0 and 10 to the 5 times the value that we observe, the Sorini and Peacock 2021 model of cosmic star formation, and that the probability of generating observers is proportional to the cosmic star formation efficiency as defined earlier, then we find that the maximum cosmic star formation efficiency is around 1/10 of the observed value of the cosmological constant, and the probability of observing a value of lambda less than or equal to the one that we do measure is around 0.5%. We are just following Weinberg's argument here. So if one sticks to that, this could put a bit under stress the anthropic principle, but certainly I'm not saying that we need to trash that, because we have considered only the simplest ensemble where we vary only one parameter, and then there are many more things that we could do to improve the star formation model, or also many other subtleties, and perhaps we can talk about that towards the end of the discussion.
0.5% is a much larger number than 1 in 10 to the 15 if one's being super conservative, and it's certainly bigger than 1 in 10 to the power of 120. So
in that sense, yes. I guess the way I was seeing it as perhaps a bit more of a challenge is because compared to the other works that have been done with the simulations, or with John Peacock's 2007 model that I mentioned in the beginning of this chat, this model tells you that would predict a much lower probability. Not much lower, but lower.
The fact that there is this meaningful drop-off at small values of lambda of your what you're calling the likelihood, the probability of generating observers, can we turn that around and use observations out there in the real world of star formation in galaxies to measure lambda?
So basically, because it depends, as I said, on the density, which depends on the virial radius, which is determined by cosmology, by the star formation rate of a halo at a fixed mass and a fixed redshift, you could infer lambda, for example.
Yeah, I mean, we can't compare two different galaxies with the different values of lambda, but we can look at a population of galaxies, right? I mean, you showed me this great Barnes et al. Picture of the galaxy with two different values of lambda. I guess that was 1 in 300 rather than 1 in 10 to the minus 3. But I imagine there's an equivalent two pictures and they'd look different. Is there some way of using that difference to measure lambda in our universe? Once you look at the population of all the galaxies we've been able to observe with such high resolution.
So I guess what you had in mind was if we know how the star, well, not asymptotic, but like a redshift zero, how the stellar mass fraction would look as a function of the halo mass, then you could use that to constrain lambda, basically.
What would this look like at redshift zero, or is this only making like a meaningful difference at very late times?
So no, you would have a difference also, a meaningful difference at redshift zero, because that's basically, as you said, what the Barnes plots were showing us. However, I think there's a lot of model dependence behind it. So if you made observations of the stellar mass fraction, I think it would probably be a bit of a stretch to measure lambda in that way, or I presume that there will be much larger, very large error bars, and there is just, I think, too much uncertainty on the galaxy formation models.
Can I not then turn that on its head and say that your likelihood function should be including that uncertainty and therefore should be much wider?
In a way, in this plot, we can see different models already with different. So these different simulations have different subgrid physics. So my curve is another curve here. So you can see that part of this scatter in the relationship is determined by the different star formation model, I would say, plus other things such as the fact that simulations are limited and all the things that I said earlier. But
yeah. So on the anthropic side of things, of is lambda less than 10 to the power of 5, the feedback modeling is adequate. But on the I'm actually making real observations now, I'm going to measure lambda. I guess one could still measure the value of lambda and say it is not bigger than some very large value, but maybe not say that it is bigger than some lower bound.
Yeah, probably something like that. Yeah.
Your probability of generating observers proportional to cosmic star formation efficiency point is not something we've discussed much. I guess in the end, you've still got a per unit volume in your likelihood there. What about the fact that bigger values of lambda are generating maybe bigger volumes over a function of time? Should one not be considering the total number of I'm not sure whether this is a meaningful question or not, but obviously it's the total number of stars you want, not the total number of stars per unit volume. So I guess you're making an assumption that the total volume is the same. I guess the co-moving volume is the same in all of these pieces of the multiverse. Is that?
So this assumption is equivalent to assuming that equal volumes of matter in the universe carry equal probabilities of generating observers. So it should be something like that. I've done the calculation for that, but you could instead weigh that on mass, or you could also consider different ways to weigh your probability measure in a way. So this is a very subtle thing as well. I would say it's equivalent ultimately to assuming a certain measure in the multiverse, and that's very much an open question.
And so how much do the results depend on changing the measure?
So Barnes et al. 2018 considered 3 possible different measures, and it turns out that they could impact the results quite significantly again. In one of those measures, they were basically obtaining that the value of lambda we observe is anthropically favored, whereas in others not as much. But again, as they do stress in their paper, it's not that you can as well select the measure that you prefer just to reach your preferred conclusions. Just like you cannot assume the prior that you prefer on lambda just to save or to sync anthropic arguments. The measure should be part of your multiverse theory. Now, exactly how that should be done, I don't know, and my understanding is that this is a very difficult problem.
Where are you going to next, and how do you think the community should change based on these results?
Well, on what to do next, one thing is for sure to try and improve the feedback modeling in my cosmic star formation model, not having only a stellar constellar wind, but also introducing more explicit AGN driven features. And because we saw from previous works, for example in Salcido et al. 2018, that different feedback models can really change the future star formation. In the case, I even found that there is a revival of star formation in the future if you switch off AGN feedback. That's not predicted in the ENSO simulations, the ones from O et al. Group, nor is it predicted by my model. But the point is that, as I was saying, there is a strong dependence on star formation on the model of feedback that you are assuming. So that's something that I may want to revisit in the future. Another point is also the connection between the likelihood of generating observers and the stellar cosmic stellar efficiency. So that could be too simplistic. There have been works, for example, by Sobral Blanco in 2000 et al. In 2020, where they introduced a delay for the formation of terrestrial planets and another delay for to allow for the evolution to occur and intelligent observers to emerge. Now, of course, this introduces other questions. For example, should really all life in the universe look like the one on Earth? And so are we justified in assuming that that's the time it takes for evolution to occur? Also, I'm not a biologist, so there are many more implications for that. So I think it's very tricky. You can make a more realistic model, but that requires also to introduce other assumptions.
But why does this delay matter? I mean, the solar system's not being destroyed. So once the star has formed, presumably the chance of intelligent life coming from that star doesn't change.
Yeah, this delay would not matter if you integrate over the entire history of the universe, but they were interested in the delay for other reasons in that particular paper. However, it is interesting to ask ourselves what stars are the most likely one at hosting, let's say, rocky planets, and where is it easier to have life emerge. So these sort of questions, and but he has said that would require other assumptions. And
yeah, I guess you were saying it requires us to assume life is like us, but we are us. So when you take the anthropic argument to its conclusion, like I'm actually asking, what is the probability that Sean Hotchkiss would exist? And that's the question I want to ask, and you want to ask a slightly different question, of course. But
well, I guess that the way I see the anthropic argument is not necessarily only us humans, but there could be other type of intelligent observers. You know, you only need a universe that promotes intelligent observers to use anthropic arguments. In my opinion, you know, there could be something that could look like us in another part of the universe or in the future, or just does not look very much like us, but is still an intelligent observer capable of asking themselves, oh, well, why are we here? Why do we measure this value of the cosmological constant, etc., etc.? And here we are really entering the philosophical questions that we were mentioning earlier. So, yeah, just the other thing I wanted to say was, of course, extending the multiverse ensemble by changing not only one parameter, lambda, but also more parameters together, and we're working on that. We're trying to change 6 parameters at the same time, in fact, and let's see what that takes us.
Yeah, getting your likelihood, I think, is relatively straightforward there, but then it does become very interesting about what the priors would be for all these other parameters. But I guess that's...
Yes, exactly, yes, yes. And finally, if we put my results into the context with the other simulations I mentioned, so the blue dots here are the results from Barnes et al. For the fraction of baryonic mass per unit moving volume converted into stars over the history of the universe, and the purple points are the ones from the ENSO simulations by O et al. And the lines here are their proposed fitting formula to these results that they got from the simulations. Now, the red line is are the results of my model. Here I simply put a logarithmic scale on the y-axis to show the other points here better. And the salmon lines are variations of my model where I either change some key astrophysical parameter or I introduce a certain cut in the cosmic time, just like in the simulation. So 20.7 gigayears is the one for the Eagle simulations, and 97 gigayears is the one for the ENSO simulations. So when you do that, you can see that you still have this peak feature, but is a bit less prominent. And my point in this plot is that it would really be interesting to run a simulation with 1/10 at this point of the cosmological constant, of the observed cosmological constant. Because who tells you that you don't have a little peak forming? We just don't have that data point. So 1/10 or anything else in between here would be, I think, very helpful to know.
You guess you didn't mention negative lambda.
Oh yeah, I forgot to say, thank you. Yeah, also I would really like to extend it to negative lambdas in the future.
I don't know whether I'm gonna leave this in the edit, but I'm gonna advertise my own work here for once. I did some super speculative work where one looks at the multiverse and just says, hey, let's just take the central limit theorem and model the parameters of the multiverse by a Gaussian random field and say, okay, there are all sorts of fields going on in contributing vacuum energy at all sorts of different parameters and scales and blah, 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 blah. And let's assume that they're independent enough that in the end you get a Gaussian random field, which is then just described by a power spectrum or a correlation function. Then you can ask questions like, okay, in this Gaussian random field, what's the probability that a minimum has this value of lambda? What's the probability that a minimum has that value of lambda? And that gives you an independent way of getting this prior. It isn't a totally flat prior from 0 to your upper limit, depending on your power spectrum and stuff like that. Of course, it kind of just pushes the question back one level. You then have to say, what is the power spectrum of my Gaussian random field, or what is the correlation function? But for different power spectrums and different correlation functions, you would then get different prior distributions in your multiverse of this Gaussian random field of values of lambda. So perhaps it might be an interesting thing to do, is to take your likelihood and then different power spectra to give you different priors and just see. You could do the thing that you said you shouldn't do, but you could say, what power spectrum do I need of this Gaussian random field such that our observed value of lambda is like the peak of the posterior, and then say, okay, string theorists, go away and tell me why this is the correct power spectrum to describe this Gaussian random field. What work being done in cosmology at the moment do you think is particularly interesting but underappreciated by the community?
Well, I mean, I could sort of selfishly say that works that are a bit more speculative tend to be a little bit more undervalued sometimes. And of course, our community is very much data-driven, and there's amazing progress being done with all these exciting surveys out there. However, I think sometimes it's good to also take one step back and try to look at the big picture and think about the foundations of what we are doing, both from the physical point of view and also mathematical. I'm thinking again about the discussions we had here with Sylvia Van Macher earlier. So I think that's about the probabilities in the multiverse. I think this sort of stuff is sometimes not given maybe proper attention.
Thanks everyone for watching. If you like this, please do subscribe and click the bell if you want to be notified of new videos, and click like to help with YouTube algorithms, both for you and the channel, because YouTube will know to recommend more stuff like this, and share the channel with colleagues. If you have any questions or suggestions, leave a comment. Otherwise, yeah, check out this video by Sylvia on the kind of philosophy of probability and how it actually does have meaningful impact on this multiverse situation and a few other aspects of cosmology. And thanks, Daniela, for the great talk.
Thank you very much for having me.